Now, in the earlier lecture, we discussed a very important experiment which gave rise to an understanding of what is going on when it enters into the superconducting state, namely the experiment on ultrasound attenuation. And that gave a clue to what is the mechanism of superconductivity. Another very important experiment which is very popular and is still today used in trying to understand the mechanism of superconductivity, or whenever one is going to understand the mechanism of superconductivity, one tries to find out or look for the isotope effect inside any material. And basically what that means is, what is the isotope effect? Basically what you do in the isotope effect experiment is that you measure the superconducting transition Tc of the material for different isotopes of the material. Okay, for example, let us say mercury has a Tc of say between 4.12 and 4.13. Okay, and this corresponds to an isotope of mercury with an atomic mass of 203. Okay, now atomic mass, as you know, is basically the mass of the ion, okay, inside the material. Okay, and it is basically the total number of protons and neutrons inside the material. Okay, and a material can have different isotopes, means that the atomic number is the same, but the atomic mass can be different. How heavy is your ion, that can vary. Okay, so you can take ions of different material, you can take isotopes of different of the same material, you can take different isotopes, basically the same material, but the weight of the ions is different, and what you will find is that the Tc will be different for each of those isotopes. So if you make your isotopes heavier and heavier, you will see that your Tc starts falling. Here is the isotope of mercury 198. You can see its Tc is between 4.17 and 4.18, and if you make the ion of mercury heavier and heavier and go up to 2.203, you will see that your Tc is much lower compared to the lighter mercury ion, lighter mass of ion, or the lighter isotope of mercury. Okay, so the Tc has a relationship with how heavy is your ion inside the lattice where superconductivity is occurring, and that relation is called the isotope effect. The Tc is inversely proportional to the square root of the atomic number of the isotope. Okay, atomic mass of the isotope. This is the atomic mass of the isotope, and you can also write that the Tc is inversely proportional to the mass of the ion which is participating in the superconducting in the element, okay, of the material which is superconducting, because the atomic mass is basically nothing else but the mass of the ion which makes up the material. Okay, so the superconducting transition temperature, and basically this is the isotope effect, that the superconducting transition is inversely proportional to the mass of the ion. So if you can take an ion with a lighter mass, then if you take a lighter mass ion, its Tc is higher, and if you take a heavier mass ion, its Tc becomes lower. Okay, so it looks like the mass of the ion is playing a role in mediating superconductivity in some way. Okay, and lighter ions give rise to higher Tc. It is more easy to generate the superconducting phenomena in those materials, and those with have heavier ions, the superconducting transition is not as high. It's more difficult to generate Tc in such materials. Okay, and therefore Tc's are very low in temperature. Okay, so it looks like the superconductivity phenomena doesn't only have to do with electrons inside the material, but the intermediate ions, the ions within which the electrons are moving around, in this lattice of ions through which the electrons are actually moving around, that ion lattice also plays a role in generating superconductivity, and that is the and this is a very crucial aspect which actually led to understanding the basic microscopic mechanism of superconductivity. So isotope effect is a very important and very useful experiment, and even till today people actually look to understand the mechanism of superconductivity. You actually test for the isotope effect. Does the element actually exhibit any isotope effect, or whatever is the material which is showing superconductivity, you actually go and look for isotope effect. You basically prepare materials, the same material but with different isotopes, and see is the TC shifting or not. So now let us look at before we go on to understanding the mechanism of superconductivity, let us look at and summarize what were the main experiments which actually gave some insight into superconductivity as a phenomena. And it is these insights which will be combined into one single picture, which is going to be the microscopic mechanism of superconductivity, or one proposal of a microscopic mechanism of superconductivity. So first was the Meissner effect. Okay, and the Meissner effect was basically related to the London's equation, where J is minus 1 by lambda square A. Okay, that was the basic London's equation, and we saw that if you write down the Gordon's equation for the London's equation, then if you write down the Gordon's equation for electrons in a magnetic field, then you can get the London's equation J is 1 by lambda square A only if you consider that the right probability current for right moving particles and the probability current for left moving particles is exactly identical. And this is true for any electron inside the system, not just one single electron, but for the entire state. You will describe the entire state with one single wave function, and you don't describe the superconducting state for every electron. You write down the wave function for the entire superconducting state, and all electrons actually inside the material are behaving in unison. Okay, so it is as if the system has developed some rigidity. The electronic state has developed some rigidity where each electron is not behaving independently and behaving randomly, but the entire system is behaving as one single entity, and the entire system has one single wave function. So as if the entire system is one single macroscopic quantum state. Okay, the system has developed that sort of a rigidity. It is like as if everything is moving coherently as one single entity. Okay, and that was the most important outcome of the Meissner effect or the London's equation, and it is only in this state that you can show that J is equal to minus 1 by lambda square A. So the entire electronic state behaves as one single coherent entity, uniformly moving as if they are all marching together. Then you go to the thermodynamics of the superconductor, and in the thermodynamics of the superconductor, we know that there is a lowering of the free energy once it enters into the superconducting state. So as if electrons are lowering their free energy, and the extent of lowering this energy scale mu naught by hc square is nowhere close to the Fermi energy. The energy is much lower than the Fermi energy. The electronic state also, once you measure the entropy of the system, once it goes into the superconducting state, it lowers its entropy. So as if the electrons are entering into a ordered state, which basically means that the entropy of the system is going to get lowered, and that you observe that once it enter into the superconducting state below the transition temperature, the entropy of the system is lower compared to the normal state. Then we came to the specific heat, and the specific heat experiment gave us two very important clues. One is that once it enters once the material is cooled below the superconducting transition, there is a jump in specific heat. This jump in specific heat corresponds to a phase transition. That is, the material is actually, or the superconducting state corresponds to a phase transition in the system, or the electronic state is actually undergoing some sort of a phase transition and going into a lower energy state where the entropy is also lower. Okay, and the jump in specific heat we interpreted as indicating that there is an opening up of a gap in the density of states. There are no single particle states available around the Fermi energy for the electrons to occupy. Okay, and this corresponds to an opening up of a gap in the density of states, and this gap in the density of states will give rise to a jump in specific heat. Okay, this was the understanding that we got from these thermodynamic measurements. Now, this opening up of a gap in the specific heat around the Fermi energy was proved by the ultrasound attenuation experiment, where we showed that, or where the ultrasound experiment showed that when you excite vibrations inside the lattice, then the electrons don't absorb. Once in the superconducting state, within energy range around the Fermi energy, electrons cannot absorb energy from the vibrations and undergo an excitation. Okay, if the energy that you're putting into the system is not sufficiently large, then the electrons do not have, if they are within a certain energy range, then within a certain energy range of the Fermi energy, the wave will propagate without dissipating energy. It will not lose energy and give it to the electrons. This is unlike a metal, where even a small amount of energy, whatever be the energy of the wave that you're putting in, there are states available around the energy, around the Fermi energy, for the electrons to get excited. So they will pick up energy from the incoming wave and get excited. So the incoming wave gives up energy to these electrons, and the electrons get excited around the Fermi energy. But in a superconducting state, because there is a gap in the density of states and the single electron density of states, there are no electrons, there are no available states for the electrons to get excited into within a certain range of the Fermi energy. So if you put an ultrasound power into the system, it will not absorb that power. Okay, and this happens only below the superconducting transition. And finally, when you go to the isotope effect, it shows that the electrons inside the lattice are not the only players which are involved in this game of superconductivity, but the ions in the lattice are also playing a very important role in mediating superconductivity, because the superconducting transition actually turns out to be the proportional to the mass of the ions inside the lattice. Okay, so all of these experiments set the stage for building a microscopic picture of superconductivity, and that mechanism of superconductivity was given by the BCS theory of superconductivity, which is the Bardeen, Cooper and Schrieffer theory of superconductivity. It was one of the theories, a very successful theory, which explained superconductivity. It does not explain all types of superconductors and all transition temperatures which are currently observed in superconductors, but at least gives a first-hand understanding and insight into how does superconductivity arise inside the material. And I will give you an overview of this BCS theory in the next lecture. Note that, as I had said, that in the first half of the course, I will be giving you overviews, physical ideas and concepts. So the BCS theory I will discuss will be in a hand-waving arguments. I will be presenting the BCS theory. In the second half of the course, we will of course work out the BCS theory in its full details. But for now, in the next lecture, I will just discuss the bare bone physical idea of how does superconductivity arise inside the material as per the BCS theory. So I will be just presenting you the basic idea and the basic physical picture of BCS theory, and there we will not work it out. Only in the second half of the course we will work out the BCS theory. Okay, so I'll end this lecture here.